I notice that in each lecture, it seems like I spend more and more time trying to fix things that I misspoke about in the previous lecture. And since today is pretty much the last lecture, for a while, I really like to avoid that, except that I really do want to try to fix something that I spoke about. I guess I was trying to give another perspective on our slogan, which started out as something like every space is a modularized space of models of a theory of a doctrine. That's how our slogan started out. And as we've been learning a little bit more fancy stuff, I've been trying to keep the slogan a little bit updated. So we started learning how there's something fancier than a moduli space called a moduli stack. That's what it's often called, a moduli stack. And I was trying to update the slogan to take that into account. And I think I fell into a bit of a trap, because I fell into the trap of thinking that space and stack are very parallel. Because I mean, in this, algebraic geometry, somebody took this phrase moduli space, and they made this fancier version of it called a moduli stack, which makes it seem like stack is some sort of fancier version of space. And maybe because of the way people use this language, it comes to mean that, but in a way it shouldn't really mean that. I mean, I was trying to show how, I was trying to talk about these concepts of theory, of a doctrine, an object of a two-category, and stack, in some sense of the word stack, object of a two-category, stack. I was trying to show how these three concepts are very closely related. Being a theory, a doctrine, being a stack, these are sometimes slightly different aspects of the phenomenon of being an object of a two-category. To help articulate this a little bit, I was thinking about what are decategorified versions of this. So instead of two-category theory, what do you have in one category theory? Well, you still have objects of a one category. Object of a category. One category is also known as a category. And I think it commented that some stack is something like a categorified version of a sheet. And theory, well, there's some ideas that maybe a theory of doctrine, maybe that's a categorified version of an algebra of a theory, or something like that. We could be very simply sloppy. So I could just leave a lot of things, my mistakes, instead of being sloppy. Great extent, but this is so sloppy, so bad, I don't want to comment on it, that I mean, I could blame it on people who start talking about moduli stacks. I don't really like the phrase moduli stack, because it's just not really very parallel to moduli space. Because stack just isn't really very much a categorified version of a space. It's more like a categorified version of a sheet. So it's almost like there's another column here or something like that. There could be kind of a space down here. And again, as with a lot of these words, I'm being vague what they really mean. So when I say space here, maybe I mean topological space. It could mean something more general than that. And categorified version of that might be something like a topos. Although again, I mean something a little bit open-ended by that. There are several actually very precise definitions of what a topos is. But I mean something perhaps a little bit more general than that. Sort of like the categorified version of the imprecise concept of space. So I guess I'm saying that maybe when I tried to update this slogan, I think I was thinking of putting in put moduli stack here, and then, that made me want to put stack here too. But that's the part that doesn't really seem good, because stack isn't really a categorified version of a sheet. it would be almost been better if I said something like every topos, you know, something that's like something that's more like a categorified version.
Sorry, you said stack isn't a categorified version of a sheet?
Stack is a categorified version?
You just said it isn't.
Okay.
You meant it isn't of a space.
Yeah, that's right. That's right. Or unless it's very vague. I mean, it's vague enough that all these things, you know, everything up here is a categorified version of everything down here. So they tend to group together like that. And
So now you have to erase the other stack.
what?
Are you going to erase the other stack?
Well, maybe you can put topos there as well.
That's what I thought.
Well, look, but nobody says the phrase was moduli topos, but maybe they should. Maybe they should. One phrase that they did say instead of moduli topos, and to me, sort of the same thing, is they classifying topos. So, they could say, well, but then this would be really tautological. So, but the idea of putting moduli topos here or classifying topos here, that's not, in a way, it's not such a bad idea. In part because of, you know, one of my earlier harangues about how a moduli space and a classifying space have some important conceptual relationship. So a moduli stack and a classifying topos, in a way, those are near synonyms. But well, I'm trying to sort of repair the way I said things, and partially because the terminology is mixed up. I really don't like the phrase moduli stack. It would be better if I had some better phrase for it, like moduli topos. But they usually don't talk this way. So the slogan's getting a little confused, and maybe it's better again if I just sort of recast it. So instead of trying to figure out what word to put here, I'll just, you know, recast the slogan so it doesn't start out that way. So it's like, and I think we already came close to this last time. It's like algebraic geometry. Well, it's like the main object of study in algebraic geometry is, if I could go to just like a space, like an algebraic variety or something like that. The main object of study in algebraic geometry, from the point of view that we're focusing on, is that it's the moduli stack, let's say, of models of a theory of the doctrine. And this idea of moduli stack and this idea of theory of a doctrine, those are really just different aspects of the concept of object of a two-factor. Meanwhile, the topos is really a specific example of a theory of a specific doctrine. But I'm using it somewhat loosely here to be categorified version of a space. Well, anyway. So, yeah.
So the doctrine is not like topoi. It's like there are a bunch of things that share a bunch of.
The doctrine is the doctrine of toposes, and each theory of the doctrine is a topos. So there is such a doctrine, and in a way, that's one of the doctrines. It's closely related to one of the doctrines that will.
Is that a model of the theory?
Model of theory would be called a geometric morphism. It's like an interpretation of the theory. It's called the geometric morphism between toposes in the doctrine of toposes. So this is roughly what has happened to our slogan by now. But it's actually also important to remember there was another part of our slogan that we had, kind of a codicil at the end originally, and it kind of said, It kind of says every space is a moduli space of models of the theory of a doctrine, and the key to understanding algebraic geometry is to identify and understand the doctrines thereof. And that's what I want to turn to right now. Because what I want to continue right now is I want to continue something we started last time, which is understanding what I've been calling it the ladder of doctrines. And understanding the ladder of doctrines, that's all about understanding what are the doctrines that are important to algebraic geometry and how do they relate to each other. And due to time shortage and stuff, I think I really want to make our ladder pretty short. I want to focus on just a few specific rungs in the ladder. And there'll basically be 3 rungs in the ladder. And so at the bottom of the ladder, the one we've been starting off with is the dimensional doctrine. I'll call it the dimensional doctrine for now. Well, okay, no, I'll say dimensional theory, meaning I'm interested in the 2 categories of dimensional theories, or dimensional categories. Those are the 2 categories down here. And then the next stage in the ladder is something that I'm going to call them Gabriel-Rosenberg theories. And hopefully I'll try to explain a little bit about where that name comes from. And hopefully I'll also explain why I'm drawing the ladder this way with these arrows there. And then there's one more thing in the ladder up here. And I get fairly precise about this. I'll quote a maybe I shouldn't get precise about this just because it makes the name a little unwieldy, but I'll call it coherently locally grained topos. So these are the 3 doctrines that we're going to be mainly interested in today. This is the one that we've been focusing on mostly in the lecture so far. We just started to talk about this one last time, although I don't think I called them by this name, so I'll have to remind us of what we learned about them under some other names that we started learning about them. And I don't think we've really got to this one yet. So, well, let me say a little bit about them. So the dimensional theories, that's where the line bundles live. The objects of a dimensional category, the objects of a dimensional theory, or the types of a dimensional theory, correspond to the line bundles over an algebraic variety or an algebraic stack. And the objects in a Gabriel-Rosenberg category, those correspond to what's called the coherent sheaves. And this doctrine, so yeah, the coherent sheaves live up to this level, the line bundles live down at this level. What lives out at this level is something called the big Zariski topos. We'll have to try to explain what that is at some point. But let's make this a little bit more parallel. I should call this like the category of coherent sheaves. And the category of line bundles. And all of these things, the category of line bundles, the category of coherent sheaves, the big heuristic topos, all of these are supposed to be relative to some particular algebraic variety, or algebraic stack, or something like that. So a category of line bundles is an example of a dimensional theory. The category of coherent sheaves, that's an example of the Gaussian-Rosenberg theory. And a big Zariski topos is an example of coherently locally ringed topos. So, well, okay. So we've said a lot about these things, dimensional theories. We're supposed to, by now we're supposed to know a little bit about how to take a theory like this and study the moduli space, or slightly more sophisticatedly, the moduli stack of models of the theory, and to recognize that as being an object that's a lot like a projective variety. That's how this doctrine is related to algebraic geometry. That's why the main theme of what I'm talking about, that you study algebraic geometry by studying doctrine, in particular this doctrine. But this is just at the bottom of the ladder. We want to climb up the ladder to these doctrines as well. And we'd like to have some motivation for why to climb up the ladder. Are there good things about this doctrine that let you do things that you can't do down here? Yes, we have to try and limit those off. And similarly, there may be good things you can do up here that you can't do so well down here or down here. So, let me try to say something about that. So, let's try to say some of the reasons for going from this doctrine to this doctrine. So there's one particular reason that we just started talking about at the end of last time, but we didn't quite manage to really finish it, so we're trying to talk more about it today. And that has to do with the issue of how, well, we're going to try to understand how if you go up the ladder, that means that you're going to a more expressive doctrine. It's like a language in which you can say a broader range of things. In particular, one thing that you can say in this doctrine that you can't say in this doctrine is you can say things like that you want. Let's get our example over here. You can say things like, well, okay, so we had an example of a theory in this doctrine that we can sketch. And it would be the theory of a line object equipped with a pair of sections, or a pair of points on the line. So we have sections as points of the line. Let's call them X and Y. And now you can think of this kind of, okay, so I've got to sketch the theory. I've sketched a dimensional theory, a theory of this doctrine. And it's okay to rewrite it slightly. I can rewrite it as 1, direct sum 1. I guess I could write that as like X and Y paired together or something like that. Here's what X plus Y. I don't know how to take them. But in this doctrine down here, we can't say that this. There's no way to say that we want this to be a surjection, a cover, so to speak. But in this doctrine up here, there is a way to say that. And that's a good thing to be able to say, because then you're sort of expressing the idea that this theory is really the theory whose moduli space is projective space. Because it's not a cover, it's a bad model. It's supposed to be. Like the dual line bundle is embedded in two-dimensional space. Embedded, that's the dual of this being a cover. So yeah, so there are good reasons why we want to be able to say that this is a projection. We can't say it down here, but we can't say it up here. That's one motivation for being able to, one motivation for going from this doctrine down here up the ladder to that doctrine. There's another good reason for going from this doctrine up to this doctrine. And let me try to describe what that other good reason is. See, there's sort of an older tradition in algebraic geometry about the way that you study projective varieties. It's considered a little bit old-fashioned and obsolete today, but it's actually a legitimate way to think about projective varieties, which is that the older tradition is to think of a projective variety as something that actually comes equipped with a specific embedding into projective space. The newer tradition is to try and make the things that you study about the projective variety be independent of any particular embedding in projective space. But the older viewpoint is somewhat legitimate, and in fact, you can sort of say that this doctrine down here is a lot like the older tradition, where the projective variety comes equipped with a specific embedding into projective space, because see, having a line bundle is a lot like having a good line bundle over your space is a lot like having a projective embedding. And so this is like the older tradition, where a projective variety comes equipped with a specific embedding in projective space. This is the newer tradition, where you try to do things independent of a particular embedding. Now, there's some further wrinkles to that, because down here, we're not necessarily dealing with just a single line bundle and its tensor powers. You have several independent line bundles that you're dealing with down here. So when you're studying a projective variety down here, it's more like, rather than just having the variety come equipped with a specific embedding into projective space, it's more like a specific embedding into a multi-projective space. Or there could be several different embeddings into projective space. And in fact, you could even sort of take, in some sense, you could try to take some universal embedding into multi-projective space. Take all the embeddings into projective space and include them all. And that way you're actually doing something that is independent of any particular, right? You're setting all embeddings into projective space, and you're really not setting any of them. So it's good that this sort of embodies the older tradition. But on the other hand, you can also sort of, the newer tradition down here, if you sort of saturate the theory with respect to sort of putting in all the line bundles that you can. And that's something called Morita saturation. It has to do, roughly speaking, it has to do with the theory of the Picard group and the Picard variety with the Picard stack of variety or stack. Roughly speaking, you may start out with some line bundles down here. You may go up here and then come back down, and you find out that you have more line bundles than you realize that you had. And so when you go around like that, you're sort of losing the dependence that you had on some particular embeddings in the projective space, some particular line bundles. So yeah, well, so there's a concept of some sort of generalized Marita equivalence when you have two superficially different looking dimensional theories down here that make it the same theory up there, or something like that. Well, okay. So now I want to say more about this phenomenon. How in the Gabriel-Rosenberg doctrine you can insist that this map be a cover, that be surjective. I want to say more about that right now. So let me try to, to try to understand this, I think it will help if I try to make a certain analogy between this part of the ladder here and the decategorified version of that part of the ladder. So there's sort of like, there's an analogy here. I guess I'll put it right down here. Dimensional theories are sort of like a categorified version of abelian groups, right? Because objects in a dimensional category are invertible, and they have this tensor product that's symmetric. So it's a little bit like an abelian group, but in a categorified way. So a decategorified version of the dimensional theories is abelian groups. I'll try the other black one. So the dimensional theories, decategorified version of that is the abelian groups. Decategorified version of this thing up here would be commutative rings. And this process would be the process of taking the multiplicatively invertible, it doesn't call it the unit group of a commuter ring, right? The multiplicatively invertible elements. And so that's a right adjoint process. And the left adjoint process for that is, I guess, just the process of the group ring. Group ring of an abelian group is a commutative ring. And so in order to understand why this is analogous to this, we have to remind ourselves of what this was supposed to be. So, well, it's supposed to be what coherent sheaves are like in relationship to line bundles. So line bundles are something that can tensor each other. That's the main thing you can do with line bundles. You can tensor them. And that corresponds to the operation in an abelian group. But when you start having coherent sheaves, it's sort of like a fancier version of vector bundles. So vector bundles, very roughly, are like line bundles. You get vector bundles by taking line bundles, but then you allow yourself, instead of just being able to tensor them together, you allow yourself to add them together. You allow some direct kind of sum. And in fact, For coherent sheaves, you really allow more general adaptation. You allow yourself to do a whole lot of kind of co-limits. Basically, some kind of finite co-limits to get from line bundles to category of coherent sheaves. And so that's the rough analogy here. This is just multiplication. This is multiplication and addition. Okay, so call the operation in the division group. Think of it as multiplication. You're more used to think of it as addition. In this analogy, it's multiplication down here. Up here, it's multiplication and addition. The analog over here is that down here, we have tensor product of line bundles. Up here, we have tensor product of coherent sheaves and colimits of coherent sheaves. That colimits is the categorical version of addition. So that's how this analogy works here. So, an important part of the analogy is that you actually do get adjoint functors here. You have a left adjoint and a right adjoint. And that's pretty crucial in having this concept of a ladder of doctrines. That's one of the things that at this point I'm pretty much insistent on. If you're going to have a ladder of doctrines, it should really involve these adjoint functors. A left adjoint going up this way, a right adjoint going down this way, and you think of it that the one at the top, the codomain of the left adjoint. You think of that as being the more expressive doctrine, the more expressive language, sort of a more powerful language, and let's try to understand a little bit why that is. So
There are also categorification maps going to the left, right? That are certain.
going to the left is them?
So like one bottom is called the card.
The card group?
And I don't know if that has a name, but
There very well may be. I didn't really think too carefully about that. But yeah, it sounds like there would be something like that. But I don't know. I can't remember what the name would be. If I ever knew what the name would be for such a process. I just don't remember how these terminologies work. But yeah.
What is it?
John's suggesting.
K-cohomology, I think it's called.
Really? I don't know.
So there's K theory that you can use three categories of coherent sheets.
It sounds like there should be. I just didn't actually learn
I
about
was
that.
trying to.
Is that who this Rosenberg is? This is Jonathan Rosenberg?
Yeah, well,
Who?
that's not who he is, but yeah, one of the things he does.
Well,
What's his name?
Jonathan Rosenberg.
Oh, maybe that's that. Yeah. Okay. So one of the things I'm trying to explain here is why this idea of an adjunction, with the left adjunct here and the right adjunct here, but particularly in this categorified version of it, why that's associated with the idea of having a more expressive doctrine on top and a less expressive doctrine on bottom. The rough idea is this: you have the left adjoint and you have the right adjoint. And you have some environment that lives in the richer, more expressive doctrine. And you have some theory that lives in the poorer, less expressive doctrine. And the basic adjointness relationship is that if you have a theory of if you have a model of a theory of the core doctrine in the underlying core theory of a rich environment, maybe I should, I'm going to try and choose these names. What? I want to say that you sort of impoverish a rich environment to make it a poor environment, and you richen a poor theory to make it a rich theory. Here's the n-rich or rich n. I just did it. And the idea is that a model of a poor theory in the impoverishment of a rich environment is the same thing as a model of the richened theory in the original rich environment. This seems to me like a fairly essential aspect of what it means to say that this doctrine is more expressive. Because we're saying that you can talk about this concept down here, which is basically a model of a core theory. You can talk about you can say the same thing up here in the richer doctrine. So that's the sense in which this is, quote, more expressive. That the kinds of things you can talk about down here, you can also talk about up here. Now, I mean, there's some sort of formal duality going on around here. So if we're making it sound like the top of the junction is better than the bottom, there has to be some sort of dual way in which the bottom is better than the top as well. And it ends up being something like that the doctrine at the bottom is more general. I guess, like...
You could just read the...
Yeah.
You read the chart saying everybody at the bottom gives you one at the top. And now you can read it the other way, saying everyone at the top gives you one at the top.
Yeah, but you have to switch your opinion between theories and environments. So, well, it's like, what are we saying? We're saying that a richer doctrine is like good for it's good for environments because there are lots more theories that you can express, that can be interpreted in those environments. But a poorer,
If you're okay, poorer doctrine is better for theories because they're more...
environments. More environments in which you can interpret them. Right. So if you manage to drag your theory down this way, then it's an advantage for your theory, because then it has lots of core environments that can be interpreted in. But if you manage to drag your environment up to a richer doctrine, then that's good for that environment, because then there are lots more theories that can be interpreted in that environment. So it's a kind of duality between greater expressiveness of the doctrine and greater generality of the doctrine. And so I mean, that's what the concept of adjointness is doing at this two categorical level. And let me put it another way. Let me try to put it another way about how does this left adjoint process, how does the left adjoint process work? How can you sort of concretely think about the process of taking a theory and richening it so that it's a theory of the richer doctrine? And there's a very nice way to think about it, which is that if you think of theories in terms of sketches, then the way that you move a theory up to the richer doctrine is you just write down the exact same sketch. Because a sketch is sort of like a categorified version of a presentation. And that's what happens with presentations when you have an adjunction. The left adjoint process just works by taking the presentation down here, and you just write down the same presentation up here. But instead of thinking of it as a presentation of a dealing group, you think of it as a presentation of commutative rank. And that's how the left adjoint process works. And so that works in the categorified context, except that the categorified version of a presentation is, roughly speaking, the concept of a sketch, like when we do a sketch of a theory over here. So if you have a theory down here, and you sketch the theory down here, you draw a picture of it by sketching, the way you move it up to here is just copy the same sketch and just interpret it in this doctrine. And more or less the same thing here, too, as we'll hopefully see. So this theory, without the covering requirement here, lives down here. And when you want to move it up to this doctrine, you just copy the same sketch, and it's now a theory that's living up here. So the exact same sketch now represents a theory that's living up here. And so it's the same theory, it has the same kind of models, by this kind of abstract nonsense over here. But if you want to sort of describe it in a syntactic way, you have to do more work, because you end up having to, not describe, you end up having to describe not just the line bundles, but also the coherent sheets. Because the greater expressiveness of the doctrine up here requires you to include all of the syntactic constructions that you have for building new objects. It requires you to generate all those new objects and include them, and that's what the coherent sheets are. And so if you take that sketch right here, which originally lives down here, and as long as we interpret the language correctly, then we get the theory up here just by writing down the same sketch. But then it turns out, in specific examples like this, we're not quite satisfied with what you get by just writing that sketch over here. We're not quite satisfied with it because it doesn't quite give the right moduli stack. It has this extra degenerate model that's not supposed to be there in the moduli stack given by projective space. So that's when we decide that we want to make the sketch look a little bit different. And we draw that sketch and we interpret it as living in this doctrine right here. And that's legitimate because this doctrine allows you to talk about colimits. This statement that this is the cover is a statement about colimits. So we'd like to understand in a little bit more concrete detail how putting this, we want to understand in more concrete detail how putting this covering requirement in here. I keep on saying covering requirement because for people who know a little bit about the next doctrine of topos theory and growth-deep topologies have to do with coverings. And I'm trying to make an analogy here. This is very similar. There are some very important analogies very nice analogies between this doctrine and doctrines like this one up here that involve topos. They have the same kinds of interpretations between the theories. The interpretations between the theories tend to be called something like the geometric morphisms, and that's very much the same kind of things that we have here. Anyway, I keep on saying covering because I'm making an analogy to growth-deep topologies. So we want to see how this covering requirement, how it concretely affects the construction of the coherent sheaves. So let me try to say something about that right now. So once again, I want to appeal to our decategorification analogy here. I want to appeal to the analogy between this adjunction between two categories and this adjunction between one category. And the reason why this analogy is useful to us now is because we know something about how you implement equations in a commutative ring. When you want to make some elements in a commutative ring equal to each other or something like that, or you want to kill off when you want to kill off an element in a commutative ring, you take the ideal that it generates, and you kill off that ideal, just as though it's an abelian subgroup. Right down here, you can kill off an abelian subgroup, and you get a quotient group. Up here, you can't just kill off an abelian subgroup. Instead, you have to kill off an ideal, and that's how you kill things off up here. And that's very analogous to what's going on here. So down here, Actually, I should think a little bit more about what happens down here when you want to kill off an object. I didn't think about that right here. But up here, when you want to kill off an object, which is the categorified version of killing off an element over here, you should be dealing with some sort of categorified version of an ideal. And that's in fact the case what it is. So there's a categorified version of an ideal, and it's sometimes called a Serre ideal subcategory, because it's a categorified version of an ideal. And we want to understand exactly, or pretty close, to what is the Serre ideal subcategory that you mod out by when you're enforcing this requirement. So, enforcing the requirement that this be a surjective map, you can think of that as being the same thing as saying that the co-kernel of this map should be 0. So we really want to kill off this object right here. So in some sense, following our categorification analogy, we want to kill off the ideal generated by this object. We want to kill off the ideal generated by that object. Except we want to do the categorified version of that. We want to kill off the Serre ideal subcategory generated by that object. Let's try to see in some concreteness what that means. So, down here, all we have is line objects. And in the equivalence between dimensional theories and graded commutative algebras, the line objects, the objects of the dimensional theory, the dimensions, correspond to the grades of the graded commutative algebra. So you can think of the thing that lives down here as a graded commutative algebra. And when you move it up here, it turns out that what you're doing really, the process of formally adjoining colons, it really amounts to taking graded modules of your graded algebra. Or if you're insisting on finite colon, it's going to be something like finitely presented graded modules of your graded commutative algebra. So that's what you get when you start out with a dimensional theory here, thought of as a graded commutative algebra, and you get something that lives up in this doctrine. What you're getting is the category of graded modules of your graded commutative algebra. So, graded modules of your graded commutative algebra. But then we want to enforce this requirement. Right, so that means there's a specific graded module that we want to kill off. There's a specific graded module that we want to take the Serre ideal subcategory, so to speak, generated by that object, and we want to mod out the category of graded modules by that object, by that ideal, by that Serre ideal subcategory. So I just want to try to see in some somewhat concrete way, but a little bit sloppy because we're short on time, I want to see what this object is that we're killing off. So I'm going to try, so these are originally just line objects. But I'm going to, but when you go up here, they turn into graded modules. So I'll try to draw them as graded modules. So I'll try to draw, first of all, the grades. So it's all the tensor powers of L is all of the objects that we have in this dimensional theory. It's all the grades in this graded commutative algebra. And now I'm going to try to draw the graded module that corresponds to this thing right over here. And it's just a very sloppy schematic picture. It's like a basis for the grades. We start out with one generator in this grade. And then we have to let these elements of the graded algebra act. And you also have to think about left graded modules versus right graded modules. You might thought that because it's commutative, there's no difference between left and right. But there is a sort of slight difference between left modules and right modules in this graded context. And in this case, I guess it really goes this way. That, like, there's the generator, and then X acts on the generator, but Y also acts on the generator.
Might want to darken those.
Try and darken.
Yeah, that's better.
Okay. And then you keep on letting X and Y act. And you get bases that look something like this. And it goes like that. So it comes out like an infinite triangle like that, an infinite wedge. And that's this object right here.
So are those dots the basis of sections of each of those grades?
You're trying to get the. I would get this horrible confusion between L and the dual of L. I mean.
No, they're not. I just think so.
L. I don't think you should think of them as. I don't know. I have to think about whether they're sections or not.
So what are they?
They're elements of these graded modules. They really are sections in a way, I guess. I mean, they're twisted sections. They're really twisted sections of these line bundles. That's really what they are.
So they're morphisms, something into
The morphisms from one line bundle to another.
from which one to which? In one example. I'll get it right. I'll get it. So one of them must be the bundle that you drew on top. Like L or L star or L star. The other one is what?
These ones right here are sections. Yeah, these right.
Those are sections from one to L.
Those are sections of L itself. Right.
Okay. Or morphisms from one to L.
Right. So these are the actual sections. These other ones are twisted sections.
Okay.
Something like that.
So there's one morphism from L to itself. That's that one dot.
Yeah.
Two morphisms from one to
That's the identity morphism of L. Yeah.
Right, yeah.
Right.
There's a basis of two morphisms from one to L.
Yeah.
Three morphisms from L star to L.
Yes. That's right. That's right. So these two morphisms, X and Y, going to this from this graded module to this graded module, it's really picking out this element and this element. So this morphism right here, before we turn it into a covering, it's really just the inclusion of this whole part into this thing over here. Because this one, the X sort of generates, that part of the wedge, and Y generates that part of the wedge, and together they generate the whole thing. So the whole co-kernel of this inclusion that we're killing off is just this little part that's left over. So it's just like that one little thing right there. So we want to take the Sayre ideal subcategory generated by this object, this very small graded module, and we want to generate the Sayre ideal subcategory generated by that. and we want to mod out by that. So you have to think about what a Sayre ideal subcategory, again, it's an analog of an ideal. So it's supposed to be closed under multiplication. So when you tensor this object by any other object, you should get something that's also in the ideal, or that also needs to be killed off. So in particular, if you tensor this by the unit object, you just get itself. But as you tensor it by these other objects, you get shifted versions of it. So all of these very short, very small, all these very small sort of atomic graded modules end up in the ideal. They end up needing to be killed off. But an ideal, I'm trying to skip details here. An ideal needs to be closed under multiplication by anything, even things from the outside. It also needs to be closed on the inside by addition. And in this case, that turns out to mean twisted addition, including twisted direct sums, meaning short exact sequence and things like that. So the whole Sayre ideal subcategory that you have to kill off is all the things that you can build up by all the shifted versions of this little tiny thing. So it ends up being all of the so-called bounded graded modules. So that's the Sayre ideal subcategory that you kill off to get to coherent sheaves. So that's sort of a theorem about what the category of coherent sheaves is like. You have to look in the book to see the details of how this theorem works. But the basic idea is you take the graded modules and then you kill off the Sayre ideal subcategory generated by this little object, this little cokernel. And that's a theorem about how to construct the category of coherent sheaves. But I really think it's my definition of the category of coherent sheaves.
So it's the Gabriel-Rosenberg theorem?
No. It's just
Sorry, yeah.
it's just some very basic theorem about how to construct the category of coherent sheaves. It's just where in Hartshorne's book where he talks about the so-called Praj construction, which is a way of getting a projective variety from a graded commutative algebra. And when you do this, how do you get the coherent sheaves in terms of the graded commutative algebra? And that's roughly what I'm trying to describe here. So it's just a very basic beginning theorem about projective varieties in terms of the so-called Praj construction. We're getting from a graded commutative algebra to a projective variety. So so let me try to say something about how to get both sheaves. Well, first I could try to answer a question that John just implicitly asked, which is, why do I calling this the Gabriel-Rosenberg doctrine? Why do I call the theories that live here? Why do I call them Gabriel-Rosenberg theories? And the reason that I call them that is that there's a theorem, or people tell me that there's a theorem. What do you think? I should actually try to look this theorem up and see if I actually understand it. But people tell me that there's a theorem called the Gabriel-Rosenberg theorem. And roughly what I've heard about it is that the Gabriel-Rosenberg theorem says that this thing here knows all about the variety, or the scheme, I'll say the variety, whatever, the algebraic variety. That you can completely recover an algebraic variety from its category of coherent sheaves. So that's just saying that the theories that live here, which are really just these categories of coherent sheaves, those are like good stand-ins for the variety, because you can recover the variety from the category. Now, I would like, I didn't check to see how this theorem actually works. I would like a really nice version of this that would not just talk about recovering the objects, but to say, you know, there's some equivalence of categories, some very nice equivalence of categories. So again, there should be the interpretations between these theories, which are, so to speak, some kind of geometric morphisms. At some point I can try to explain what I mean by that. That the geometric morphisms between these categories of coherent sheaves, that those should correspond to the algebraic maps between the varieties or the schemes. So that's roughly what the Gabriel-Rosenberg theorem says, according to what I've heard. And the reason I call this the Gabriel-Rosenberg doctrine, and these things the Gabriel-Rosenberg theory, is because I'm just following the practice of trying to promote, or demote, depending on how you look at it, a theorem into a definition. You know, if I define the algebraic varieties or the algebraic stacks or whatever, if I define them to be this kind of category, and I would like to say more precisely exactly what kind of category I mean. At the moment, I'm just saying that it's like the category of coherent sheaves. Basically, it could mean that it's got nice colimits, it's got nice tensor product, and probably there should be some fine print about the objects being coherent or something like that. But I don't have time to go into detail like that right now. But if I just define the varieties to be these theories in this particular doctrine, then the Gabriel-Rosenberg theorem is sort of true by definition, right? So that's why I call this the Gabriel-Rosenberg doctrine. So I really like this doctrine. I think, in some sense, I really think that algebraic geometry, insofar as I understand it so far, really lives mainly at this level here, at this doctrine. This seems like, at the moment to me, it seems like the most important doctrine in algebraic geometry. The thing about this doctrine is that it's so incredibly simple. It's like, right, it's way at the bottom of the ladder, almost literally, right? It's like a good way to start climbing up the ladder. These things, they're just so incredibly simple. They're just greatly iterative algebra, really. But it's really important to think of them as theories, and that prepares you for understanding these more complicated theories up here. So this is the great halfway house, the great rung on the ladder that's close to the ground when you're trying to climb up this ladder to where algebraic geometry mainly lives, which I think is right here. Although maybe there's all even more fun stuff going on. I don't know. I don't know.
That's where he disappeared to.
There's a whole bunch of other intermediate ones on the ladder. I'd love to talk more about those. There are other parallel ladders. I'd like to talk more about those. And the ladders aren't just purely vertical. They go up the sides too. This is the doctrine where I think algebraic geometry mainly lives. Which does invite the question of, what is this doctrine really for? And I'm not sure I really completely understand all the things that this doctrine is for yet. But we'll try to get to that. Really good about time. Well, this is the doctrine where I think algebraic geometry mainly lives. And this doctrine is a great halfway house. It's a great low rung on the ladder for learning purposes. And perhaps going along with that, it also represents this older tradition of algebraic geometry, where you think of a projective variety as equipped with a specific embedding, or perhaps several specific embeddings into projection space. So the older tradition and the newer tradition, roughly speaking. And some even newer traditions don't really understand it. So let's try to say a little bit about what this doctrine is. Well, we have to again use our principle about how these adjunctions work, how they represent a more at the top you have a more expressive doctrine, at the bottom you have a less expressive doctrine. So now this is our less expressive doctrine, and this is our more expressive doctrine. And we have the same principle that the way to get up from the less expressive doctrine to the more expressive doctrine is that you take your sketch and you just copy it, but now you interpret it as a sketch of the richer doctrine. So in order for that to work, you have to know how to interpret the sketches of the poorer doctrine as sketches of theories of the richer doctrine. So the language has to make sense in the richer context. That's, again, that's an aspect of what we mean when we say the doctrine is more expressive. So what is a ranged topos? A topos is a theory of a certain doctrine. It's a very nice doctrine. You can say that it's the doctrine of set-like categories. It's the doctrine, very roughly speaking, it's the doctrine of categories that have limits and colimits in a way that very strongly imitates the way that limits and colimits exist in the category of sets. Mainly you deal with finite limits, and then possibly finite colimits, or possibly more colimits. And that's what a topos is. A ringed topos, it can really be called a commutatively ringed topos. Let's see, here I'm talking about locally ringed toposes. A ringed topos, it's a theory that's an extension of the theory of commutative rings. So it's kind of like this. It's kind of like how do you take a sketch down here and interpret it as a sketch up here? Well, you have to think of the sketch down here, you have to think of it as sort of an addition, a sort of codicil to the theory that you already have up here. So like built into this doctrine here is that you need the theory of rings, the theory of commutative rings, or actually in this case, the theory of local commutative rings. You have to find out what those are. The theory of local commutative rings. You sketch that theory, but once you sketch that theory, you can then sketch other things added onto it. And so those additions, those extras that you put on, beyond the theory of local commutative rings, that extra sketch, part of the sketch, that's what the locally ranged topos is. Coherent is some sort of technical detail we don't have time for right now. So the point is that a sketch in this language, it talks about tensor products and direct sums and stuff like that, and co-kernels and things like that. And you might not think at first that syntax makes sense in this context, because topos are like set-like categories. Sets, they don't need to have like tensor products and not those funny co-kernels, like the feeding thing. But the point is that once you have a commutative ring in your topos, then that gives you a way to interpret the things in this doctrine as making sense in this doctrine. So what?
As modules.
Yes. I mean, you get.
So the guys down below got the modules.
Yes. And maybe even a better way of saying it is that if you have one of these rich environments and you get the poor environment from it, you get the poor environment by taking the modules of your ring object. That's really another way of saying, I think, what both of us are trying to say here. So that's a very sloppy way of saying it, but roughly speaking, that's what happens. There's the same way you go from the category of line bundles to the category of coherent sheaves. If you go up to this even further doctrine, by again just copying your sketch and interpreting in this new language, new more expressive language, it gives you more stuff up here. And that's called the big Zariski topos. Now, there was no way I was going to be able to really say much about what I really did this for anyway, even if I did have time. I'll just give a stupid hint about what I think may be going on. There's lots more interesting things to say, but we're out of time. So, this is where algebraic geometry, as I understand it, really lives. And this seems like something extra. And sometimes I heard what it's for. There's a whole lot of other ways that topos theory enters into algebraic geometry at a sort of very fancy, high-pitched level. And stupid guess, that has a lot to do with the homotopy theoretic aspect of algebraic geometry. Toposes are categorized by topological spaces. That's one somewhat accurate slogan. And topological spaces, that started out being where homotopy theory lives. So, that's really a good thing. But maybe things that are going on here have a lot to do with the homotopy. Maybe there are ways of understanding homotopy theoretic aspects of algebraic geometry that have to do with this. Let me try to finish up in my 2 minutes left. Let me just try to, I don't know, sum up or say all the things I've got to say. So, I started learning topos theory a long time ago, mostly from Lovier. And it was great. I loved topos theory. But I originally thought that when I was learning topos theory that I was going to learn algebraic geometry from it. Because, I heard that there was this interaction between topos theory and algebraic geometry. And it didn't work out that way. I learned lots about topos theory, but it didn't seem to help me learn about algebraic geometry. Because topos theory for its own sake went off in its own direction. In some ways, a lot of ways, led by Lovier. And so it was like there were two cultures of topos theory. One which has to do with its original algebraic geometry inspirations. And the other one went off in its own direction, which was great, but it seemed alienated from the original direction. And I was disappointed with this alienation between the two cultures of topos theory. And in a way, I'm trying to reconcile those two cultures right now. And there's a whole bunch of other ways in which what I'm trying to do is inspired by and affected by things that Lovier did. This whole idea of dimensional theories and how they're related to graded commutative algebra. I remember Lovier talking about that a long time ago. I didn't understand what he was talking about at the time. I don't remember him explaining how that was really secretly what algebraic geometry was all about. But maybe he said that too. I should know that. There's a lot of other things that, like I say, were sort of influenced by Lovier's ideas. But on the other hand, when I read what Lovier says, he reflects about the people he was influenced by, like John Beck and Gertrude. So, I don't know. Anyway, I'll stop there right now.